Welcome, my dear students, this new class. In the last class, we discussed about the basis and prove some important result related to the basis. In this class, we discuss about the dimension of a vector space. Dimension of a vector space, we need a basis, and this means the number of element in the basis is the dimension of a vector space. So for a basis, you already know that for a basis, we have a basis means we have a two things compiled with. If basis means one is a if any set B is a basis. So if B is linearly independent and span of B is equal to, you have to just say that uh, span of a B is equal to V, generate all this. So let V be a vector space. The number of vectors in any basis of a V is called the dimension of a V and denoted by dimension of a V in this form. So this means we clearly say that, for example, if we take a vector space, we take a for the moment is equal to R2, and we choose a standard basis. E1 is equal to, you have a 1 0, and E2 is equal to, we have a 0 1. Then we have a this set is equal to this E1 comma E2, and clearly this set is linearly independent, because if we take a final linear combination of these two set plus beta times 0 1 is equal to 0 vector in R2. So this means this is equal to alpha is equal to 0, trivially beta is equal to 0, and also if we take x and y is the any element of a R2, then this x and y can be written in the form of a linear combination of these two elements, and then you have y times 0 1. So this implies that this means say that we can say that clearly the this set basis. So we have a span of B is equal to, you have a R2, and or we can say that span of this is equal to, we can say the span of a this x and y is R2, and also B is linearly independent. So this B is from a basis, and this basis has a two elements 1 and 2. So this means we can say dimension of R2 is equal to 2. So we have to say that dimension R2 is equal to 2. Now next we say that the elements, if the number of element in the basis is finite, so we can call is a finite number vector, then we can say that is finite dimensional vector space. And if a vector space has a n number of elements, then we say that the dimension of a V equal to n, and we write dimension of a V is equal to n. Like the previous example, we have a dimension of basis has this 1 0 and 0 1. There is a only two elements, and then the dimension of this vector space V is equal to, we have a R2 is equal to 2 is there. So if it is not a finite dimensional, then we consider that is called is a infinite dimensional vector space. For example, if we take a zero dimension vector space, and if vector space we have only this 0, that means 0 is clearly this set is a linearly dependent and has a basis has a no element, and if basis has a no element, then we can say that the dimension of a 0 vector space is a 0. Okay, so because this is a linear dependent, so no vectors in the basis of this, which means that it has a dimension 0. Suppose we take a V is equal to non-zero vector, and V is only this non-zero vector V, this is a set, and we know that the property, if V has a singleton non-zero vector, which is always is a linearly independent, and also span of this can be written as a finally alpha times of a V. This is clearly all these things, and also we have to alpha V is equal to 0, means alpha is equal to 0, or we have a V is equal to 0, but we have a given V is not equal to 0. So this means only possibility is alpha is equal to 0. So we can say that this clearly is a linearly independent, and also span. So this is the basis, and then the basis is only one element. So this means B is only this element of 1. So that means one vector. So this means we can say that the dimension of this set wholly V is equal to 1. So if we have a singleton non-zero element in a vector space, then we can say that this vector dimension of such a vector space is equal to 1. Okay. This means we clearly just say now we have to move to the example for we have to try to find the dimension of R3. So again we have to collect the standard basis of R for R3. For example, E1 is equal to 1 0 0, and we have a E2 is equal to we have a 0 1 0, and we have a E3 is equal to 0 0 1. So this is a standard basis. Clearly they form linearly independent, and also suppose we take a B is the vector in the form of a E1, E2, E3, and now we have a clearly span of B is equal to V, because X, Y, Z any element into the R3, then X, Y, Z can be written in the form of X of 1 0 0 plus Y of 0 1 0 plus Z of 0 0 1. So this means this generate. So this means it's X, Y, Z can into the basis can generate into this. So this means span of a V is equal to V. V is equal to you have a here R3, and also these are the linear independent. If we take a write a linear combination of a this is equal to 0, is trivially alpha 0, beta 0, and gamma 0. So this B is clearly is you have a linearly independent, and basis span of a B is equal to this form a clearly is a basis, and in this basis we have a 3 elements. We can say that dimension of vector space R to the power 3 is equal to 3. So that is means okay, just we just write into this form. So dimension is equal to 3. So by this because you see we have to show that dimension of R2 is equal to 2, and we show that dimension of R to the power 3 is equal to 3. In the similar fashion we can say that in general vector space of V is equal to R to the power n. Then the dimension of this vector space is equal to n. Use the solution is similar way. We can just take a standard basis. Standard basis, we have to take a B is equal to we have a E1, E2 up to En, and we have to just define Ei is nothing but is equal to form of a 0 0 some 1, and we have a 0 0 means ith position is this is you have a ith position a 1, and the rest of the element is equal to 0. So here we can say that similarly E1 is equal to 1 0. So we can write E1 is equal to 1 0 0 and 2 0, and that is equal to n elements, n vectors because of this. And similarly we can write E2 is equal to you have a 0 1 0 0, and in the same fashion we can say that En is equal to 0 0 and so on is equal to 1 is nth position. Now clearly this xy is up to we can write this is written in the form of x. We can write any vector of a x1 x2 up to xn. These are the element of a r to the power n. Then this vector x1 x2 up to x to the power n can be written as a x1 e1 plus x2 e2 and so on xn en. So this means we can say that in generally span of b is equal to v is equal to r to the power n, and also this criterially b is linearly independent. So this means this form, this means this is total number of element in this basis is equal to n. So this is a n vectors. So this total basis has a n element. So this means we can say that in general dimension of r to the power n is equal to n. So we just say that if we have a any vector space, if Rn we have a clearly the dimension is equal to n is there. Let us try to some different example for a polynomial. So we just this is the way we can just say that. So polynomial, we start from the polynomial of a degree 2, and the polynomial of a degree 2 means we take any arbitrary of the elements of this the form, this standard basis from this basis b is equal to the form of a 1 x and x square. These are the extended basis, because any elements of a P2 can be written in the form of a a0 a1x a2x square, where a0 a1 a2 are the element of a real. So if a basis if this is the standard basis, because trivially this is a basis. Why? Because we take any element of a0 plus a1x a2x square is the element of a P2, and that means this element can be written in the form of a, so a0 plus a1x plus a2x square can be written in the form of basis of a a0 into 1 a1 into x plus a2 into x square. So this means this vectors, any arbitrary vector from this can be written as a linear combination generate whole the basis. So this means we can say that span of this b is equal to, you have a P2, and also this is clearly linear independent. We can write alpha into 1 plus beta into x plus gamma into x square is equal to 0 into 0 plus 0 into x plus 0 into x square. Now this giving alpha is equal to 0, beta is equal to 0, gamma is equal to 0. So this is a clearly linear independent and also generate. So this is the basis and this is the standard basis, and in this basis you have a 3 vectors. So in this basis is a 3 vectors. So we can say that dimension of P2 so we have dimension of P2 is equal to 3. So like this so this I just take into this form. So this has a 3 elements, and this means this 3 elements, this dimension of a P2 is equal to 3. So same way we can generate this for a polynomials of p to the power n. Pn, we can Pn, you know that Pn can be the written in the form of this a naught plus a1x a2x square plus so on en(x) to the power n. So the previous one, we again assuming the standard basis, b is the form of a 1 x x square x to the power n, and this is clearly linear independent, and also this vector can be written in the form of a this into 1 into this in this form. So this form generate this and also is a linear independent. So this is clearly linear independent, and span of b is equal to, you have a Pn, and then this have a, you have a n plus 1 elements are there. So this means we can say that dimension of a Pn is equal to n plus 1. So that means we can simply say that dimension of this again is a we prove is Pn is equal to n plus 1. Okay, so this means we can just choose a standard basis, and the polynomials this can be written in this form. So this means a linear combination of this of the 0 vector again always is giving all this is equal to 0 scalars. So this means is a, because there is a this is a n plus 1 vectors. So this means we can say the dimension of this is clearly is a n plus 1. Now we just try to example for matrices. We take a 2 by 3 matrices. So if we take it 2 by 3 matrices, we choose a basis of this in this form, because it's a 2 by 3. So we have a 3 columns and 2 rows, 0 0 0, and then we have a 0 1 0 0 0 0, and then we have a 0 0 1 0 0 0, and then now we have matrix 0 0 0 1 0 0, then we have a matrix 0 0 0 0 1 0, and now we have matrix 0 0 0 0 0 1. Now clearly this set we have to assume is equal to b, and this whole set can be written in the form of this A, B, C, D, F and G, and this can be written in the form of a times of a 1 0 0 0 0 0 plus B times you have a 0 1 0 0 0 0 plus C times of a 0 0 1 and 0 0 0, and then plus you have a D times of a 0 0 0 1 0 0 and plus F times of a 0 0 0 0 1 0, and we have a G times of a 0 0 0 0 0 1. Clearly this any 2 by 3 matrix can be written in the form of a this is the element of a clearly M of 2 by 3 matrices, and this can be written, and this is clearly also is linearly independent, this giving 0, this giving 0, scalars are 0. So this is clearly you have a this set is a linearly independent, and also spin of this B is equal to you have a M of 2 by 3. So this set is form a basis, and in this basis we have a 6 elements. So we can say that clearly dimension of M of 2 by 3 is equal to 6, and this is nothing but is equal to 6 into 2 into 3 times. So number of rows into number of columns, the dimension of a such a matrix which is form a basis is the number of element in this is the 6 elements are there. So this means a standard basis. These bases are called the standard basis for where matrix single one and rest of them is equal to 0. We have to like this one. So this is clearly. So in general, if we have a matrix is M n by form, so we just construct a matrix for M by n. So this means you have a m rows and n columns. Then we take a simply is equal to the previous one 1, and rest of them is equal to 0 form. So generally we just construct into this, and this is the form. Now we try to some different types of a example, and now try to find what is the V is equal to, we have a M 2 by 2 matrices, and X we have to choosing is a matrix is a this form. Now consider a subspace of a this. Now we have to find the this. First we check is this is a subspace or not, and clearly you can just check you have a AX AX 0 0 matrix is always is there, 0 x is equal to x 0 is there. So this means you have a no problem. This is additive identity is there, and if we take a some U and V are the element of a W, and if we take a not for this matrix X, we have any matrix we take any 2 by 2 matrix, this is true for a subspace, not only particular for this type. So any types of a 2 by 2 matrix if we choosing X, and this condition Ax is equal to xa, this is clearly set a satisfy the subgroup conditions. Like this we just check if you want we can just check a U plus V also W. This means U plus V means W means any element of a belongs to the to W. So U is the element of a W means there is an element of this Ax plus Bx is equal Ax is equal to V. This we take a two matrices like this. We take a some matrix A, and B is the element of a W. So we have a Ax is equal to Xa, and we have a Bx is equal to Xb. Now we try to A plus B and then X. Because of the matrix addition, we can say that Ax plus Bx, Ax is equal to Xa, and plus we have a Xb, and then we can write this as distributive property of a matrix addition. So we can write X into AB, and this is nothing but is equal to A plus Bx is equal to X times A plus B. This implies that A plus B is the element of a W. Now if alpha is any scalar real, because we have to working in the real field, so we just say that alpha A, we have to just take alpha times Ax. So this means nothing but is equal to, we have a right in the form of a sorry we take a alpha Ax, this can be alpha times of a Ax, this is nothing but alpha times of a Xa, and this is because X can be written as a matrix. So this form the X times alpha A. So this implies that alpha A is also the element of a W. So this means clearly this W is a subspace of a M by 2 matrix with the condition of a this. Now, if this is a subspace of this, for finding the dimension of a W, we have to find the if this set is a linearly independent or not. We have to write the linear combination of this matrices of this form, all 2 by 2 matrices. So we have to take this. So W is clearly any choice of a matrix of X. X is not a choice of a matrix. So if we try to write the further what is the span of this. So we have to choosing A is the form of a this is the element of a W. If is the W, then with the condition AX is equal to XA gives that. Now if X is equal to this form, so we have a is equal to, we have A B C D, and then you have a 1 1 0, and that means this can be written in the form of this. You have a and then you have a 0, and then you have a, and then you have again 0, you have C, and then you have a C is this types, and now we have a 1 0 0 sorry 1 1 0, then we have a B C D, and this is nothing but is equal to, if you take this 2, so you have A plus C, and then you have this is equal to this, you have B plus B plus, you have a B plus B plus D, and then you have a 0 and 0. Now these two are the same, so this means you have a CC is equal to 0. So this means we have a, in this form we can just write into form of a, this is your a, and then you have a like this. So we have a C is equal to, this implies that you have a clearly C is equal to 0. If C is equal to 0 means you have a is equal to 0, and also you have a B plus D is equal to 0. So you have a the matrix of the form of a this form. So C is equal to 0 and A is equal to, you have a B plus D types is there. So this means you have a just this this is A is equal to, you have a C is equal to 0, A is equal to A, then this means you can say that sorry, this is we can just say that C is equal to 0, so you have A is equal to B plus D element from here, this 2, and this is the same because C is equal to 0, these two elements are the same, so we have to equating these two, so we getting C is equal to 0 and A is equal to B plus D types elements are there. So this means each matrix of A can be written in the form of B plus D, B and 0 D. So this means we take a B, this matrix, this. Now clearly these two matrix, this means this matrix with the condition AX is equal to XB is generating this. So this means span is so W is equal to span of a B. So B is equal to this. Clearly these two vectors are linearly independent. Why? We have a 1 1 0 0 plus we have a beta times you have 1 0 0 1 is equal to, you have a 0 0 0. So you have to just say that alpha plus beta is equal to 0, then you have a alpha is equal to 0, and then you have a beta is equal to 0. So this means this clearly alpha is equal to beta is equal to 0. So these vectors are linearly independent also, and also span is there, that means this form is the basis, and in the basis we have a two elements, so two vectors are there. So dimension of this W is equal to, we have a 2. So we can say that clearly B is independent, so dimension of this is equal to 2. So we can just prove this set the dimension of a W is equal to 2 is there. Okay, so now we have one more questions for the subspace. We take W is equal to this form. So if condition is this, X plus Y plus Z is equal to 0, so we can Z is equal to minus X minus Y. So if we take X is equal to A and Y is equal to, we take a B, then W is the form of a, you have a of the form of a this, X is equal to, you have a Y is equal to B, and Z is equal to, you have a minus A minus B, such that A and B are the element of a R. So this means this A B minus A minus B can be written in the form of a, you have to write this in the form of a like this, A times of a 1 0 minus 1, and then we have a plus B times 0 1 minus 1. So this we have like this so So this can be written in this form. So we can say that span of, or this means these are the two elements, and then clearly we write B is the element of a 1, 0 minus 1, and 0 1 minus 1, and just you clearly see these two vectors are linearly independent. Why this is linearly independent? Because none of them is written as a scalar multiple of other, or also we just tried this two vector is a linear combination of this thing. So this B is, we have a clearly linearly independent, and also we have a span of this B is equal to, we have a W. So this is equal to this, then we can say that there is a two elements. We can say that dimension of this W is equal to, we have to just say that is equal to 2. So we just take a dimension is a subspace, but initially dimension of a R3, you know that dimension of a R3 is equal to 3. We already know the dimension of a R to the power n is equal to n. So in this case, we can say that W is the subspace of a such a type. Then we show that the dimension of a W is equal to 2 is there. So W is a subspace. We can easily verify that, and then this can be this into this form, and basis elements are there, and these two vectors are clearly linear independent. So this means we can say that dimension of W is equal to 2 is there. Okay, so now one more we have to try like this. We have a this example, find the dimension of a W is equal to a plus b x square, and condition is equal to this, and now you know that the dimension of a P2 in general is equal to 2 plus 1 is equal to, we have a 3 in the basis 3 element. Now we try to what is the dimension of a W. Clearly W is a subspace because 0 plus 2, 0 plus 0 is belongs to the this Px W, and if we take a sum of any two vectors again belongs to W, and scalar multiplication is also W. So this clearly under this condition the W is a subspace. Now we try to because we have a condition is a plus 2b plus 3c is equal to 0. So this can be written as a is equal to minus 2b minus 3c. So if we have a b is equal to we take some alpha uh, alpha, and we have to take a c is equal to some beta. So W can be written in the form of a W can be written in the form of a, we have a elements of this types. We have a a, a is equal to, you have just say that minus twice beta, or we can just write the same, no need of this, we can write in the form of this. So b a is equal to minus 2b minus 3c plus bx plus c x square, such that a b sorry b and b and we have a b comma c is the element of a R, and this can be written in the form of a, we take a b, you have a written is a minus 2 plus x plus c minus 3 plus x square, and then this can be written in the form of a this is nothing but is equal to, we can say that set is p is equal to the form of this, we have a x minus 2 x square minus 3, and then just check this clearly these two vectors are linearly independent because none of them is a scalar multiple of other. So if one of them, if one is not a scalar multiple, this is clearly this is a linearly independent, and also we can just write the a0 all these things linear combination of this in this form. So this is generating into this form also. So this is means span of span of this thing element of a W is nothing but is equal to B, and then this is the element of this is equal to 2. So we can say that dimension of a W is equal to 2 is there. So just we have to just verify, and then we getting into this form, and this minus 2 plus bx into this form, and then b is equal to, there is a no need of this bracket, I think so. Okay, we no need of bracket of this, these two vectors, and then there is only two vectors are there, and if these two vectors are there, then we can say the dimension of a W is equal to 2. So this way we can calculate the some standard dimension of in this lecture r to the power n p pn, and also in the matrix form of any matrix m by n. Dimension of a r to the power n in general is common dimension is n. Dimension of Pn is n plus 1. Dimension of Mn time matrix Mn matrix is equal to m times n. And we have to discuss in the end some uh, dimensions of some subspaces of a given vector spaces. So that's I think you have to now understand how to calculate the dimension of a given vector space. So we need a dimension. First we need a basis, and clearly number of the element in the basis. We have to count the element in the basis, and then we write the dimension of it is. Okay, thank you very much. In the next class we continue some important results regarding the dimension of a vector space. Thank you for the next class.